Finance is about making rational choices in an uncertain environment, the economy. Making models of the future of the economy is not an easy task. In the natural sciences, the laws of nature do not change. This means that one can perform experiments many times in a controlled and reproducible manner, learn from them, and then make reliable predictions. In an artificial system, such as the economy, when an intervention is made, the system changes. Therefore, implementing a particular economic decision is a one-time experiment. This lack of reproducibility makes modeling and prediction a very difficult task. Nevertheless, we have a very powerful ally: data. In this course, we will use recent financial data to make models of the future. Simulating from these models will allow us to measure the risk of an investment portfolio. We will use Monte Carlo techniques to simulate scenarios and assess how future events could affect the value of the investment. The potential impact of these scenarios will help us understand the types of risks to which our portfolio is exposed. Understanding these risks is the first step in making informed and safer investment decisions. This is the time series of daily closing prices of IBM in the New York Stock Exchange. The time series looks rather irregular, with lots of ups and downs. Despite the randomness of the series, there are regularities that we can model. To uncover these regularities, it is useful to work with a series of log returns, which is obtained by log differencing the original series of prices. Log differencing is one of the standard transformations to preprocess data in time series analysis. Not only that, when we look at the unconditional distribution of log returns, we see that it resembles a Gaussian. In fact, the normality of the log returns is one of the hypotheses made by the Black-Scholes model. If we test the hypothesis that log returns are normally distributed, we see that it is a good first approximation. However, empirical log returns have heavier tails than what the normal model predicts. This means that the probabilities of large increases and of large losses in value are underestimated in a normal model. Since these events are those we want to capture to quantify risk properly, it is important to make models that are more accurate at the tails. For instance, here is a model in which we assume a student's t-distribution for the log returns. Our portfolio will invest not only in assets, but also in more sophisticated financial products, such as options. Monte Carlo methods are especially well suited to price these products. For instance, here is a Monte Carlo simulation to price a European call option. To benefit from diversification, our portfolio will invest in different assets. Changes in prices of different assets are not independent. This is especially true when there is a crisis and all assets seem to move in unison. It is therefore important to model also these dependencies. A simple way to do it is to use a multivariate Gaussian to model the joint distribution of log returns. Alternatively, you can use the theory of copulas to make more sophisticated models of these dependencies. In this course, we will put all these pieces together and build a model to measure the risk of a portfolio that invests not only in assets, but also in derivatives such as barrier, European, Asian, and basket options. How to measure the risk of such a portfolio is the subject of the final chapter of this course. Before that, we have some hard but fascinating work to do.